Okay, this afternoon Jonathan Aylen is talking about Bloodhound on my trail, building the Ferranti Argus process control computer. Jonathan's a senior lecturer in the Manchester Institute of Innovation Research at the Manchester Business School, and I asked him how he became interested in this story, and he told me that it began with an interest in process control, particularly in the steel industry, and he then developed the research from there, and he'll say a little more, I think, about that at the beginning of his talk. So can I, at this point, invite Jonathan to talk to us about Bloodhound on my trail.
Okay, well, thank you very much for inviting me. I come here with a great deal of humility because there are people in the room here, Mark for instance, who've actually programmed Argus and taken it to pieces. There's a formidable array of technical knowledge in this room which I certainly wouldn't pretend to have. The limits of my skill were once being able to write fairly fluent Fortran, and that's about it. What I hope to be able to do, the ICL extended version, what I hope to be able to do is put Argus into context, a bit of history, even some sociology, that will take it and try and put it, for the first time I think, into some kind of historical perspective. For those of you who did have a good lunch, and thank you very much, and fall asleep, this paper has actually recently been published in the what used to be called the Transactions of the Newcomen Society. If you'd like to collect a card from me at the end, I would only be too glad to email you a PDF version, and I even have some spare copies, so if you do doze off, no worries. Okay, how did I get interested in Argus? Well, of course I'm working in Manchester, so you would say it's in the water, but it isn't. What happened is that I have a long-standing interest in the steel industry, and one day, about 11 years ago, a friend of mine, Mick Steeper, said, what we're really looking for is someone to open a conference on process control. And I said, well, for all my limited knowledge of rolling mills, I know nothing particularly about process control, but I tell you what, I wouldn't mind having a look at the history. And this led me to get involved very deeply into how the GE 412 computer, which was designed by Steven Spielberg's dad, came to end up in Llanwern of all places. And loving a good shaggy dog story, I thought I'd find out more about Argus. And ended up at dinner one night about 10 years ago, sitting opposite Dr. Tom Lunt, the personnel director of Ferranti, who started telling me all about Argus. And of course you get hooked, but as those of you who've written history know, it takes a good decade before you get to the truth. So you're going to discover some rogues and a bit of scandal on the way, because I'm going to introduce you to some of the figures concerned, male and female, because one of the things that I was anxious to do was to put the female contribution on record as well as the male. I didn't want to, so to speak, an exclusively gendered history, because it seemed to me that women have been neglected in this story. Okay, why should I try and persuade you to listen to a paper on the Ferranti Argus for an hour? I think there are a whole host of reasons. First of all, I'm interested in this hinge of history when the world switched from analogue to digital. And in truth, it's been a very messy switch. It's come extremely late to, for instance, consumer durables, but it began at a very early stage in areas such as defence and process control. So it's natural that if you want to see this dramatic world shift, that you go back to try and find those who were involved in the very early decisions to go from servos and resolvers into digital control. There's also a fascinating story to this computer, that it was simultaneously both used for military, and as you'll discover was top secret, and at the same time was being used in a civilian context. And what is even stranger is the same people were involved in developing the top secret work of who were going out and trampling all over ICI Solvay plants. Of course, there's a lovely myth about spin-out. We all benefited, didn't we, from military effort in the Cold War? It all spun out into the civilian realm. That's much too simple a story. In what actually turns out to be the case, it's to do with accident, friendship, who drinks with whom. Nothing different, nothing new there. Spin-out is a convenient myth, a bit of spin if you'll pardon the obvious joke. I also want to explain something else that people don't get, which is the fact that when you read the books on the history of computing, they suggest it's somehow monolithic. Those books in the library are all about mainframes, aren't they? But if you look at the history of computing as an outsider, what you see is quite a different story. You see a bit of a story about mainframes, sure, but the process-controlled computers tend to get neglected, although I was delighted when Simon's book on Elliott automation finally hit the bookshelves. But there's also military computing, there's also computing for aircraft, and there's going to be surely a growing interest in computing for service industries, particularly, for example, telecommunications. So I think we need to rewrite the history of computing. It's not just about mainframes, it's not just about IBM. I'm also keen in finding out how technical progress happens, how innovation actually happens. So I'm interested in how communities of engineers get together. So those of you who rebuilt the Pegasus, those of you who are rebuilding other computers, know this in your heart of hearts, that what you do is you get a small group of people together, you work all hours of day and night, you drink together, you gossip like mad, lots of gossip and scandal, and respect is won on the basis of who is technically most competent. Sociologists call that the community of practice. You know that's how restoration schemes are done. You know that's how you commission computers in the past. I want to show that and reveal that with people. And finally, I am slightly ashamed at the neglect of Argus. The Manchester Museum in particular has been spectacularly unhelpful over this project, and I would like to put that on record. No one wants to know. They have 3 Arguses, they won't even let you see them. No one wants to know, but it seems to me that this is a story worth exploring, and boy would it make a great display in a museum, because you could actually set out and get kids controlling things. Okay, the beast that we're talking about, and this is a photo of the Ferranti Argus 200 as it became known in H2 lab at Wythenshawe. More about Wythenshawe in just a moment. And what you can see is a computer with some analog to digital conversion here, some memory and some racks of memory, more about that later, and some tape out for averaging things and recording things. A rather dull looking cabinet, let's be honest. But actually, although this Argus 200 sold relatively few, was the beginning of a family of computers which became a British success story. Now, Simon has said that what we got in the history of British computing is a history of failure. There are books with failure in the title. That's because people have not looked very far at, say, the success of Elliott Automation, or say the success of Ferranti in selling Argus. That these, in terms of process control, the UK and the USA arguably led the way, and there's a long history of development and use, and at the very end I'm going to appeal for information on Arguses that are still working, because they are still working in earnest and still being maintained. So this is the story, if you like, a British success story, just like the story of Elliott Automation. But why has it not figured in the books? Well, I think there are perhaps 3 reasons. The first one is we're dealing with a different part of Ferranti. We are not talking about Gorton or West Gorton. We're not talking about Peter Hall's empire. We're talking about Wythenshawe, South Manchester, near the airport. And as you probably know better than I, Ferranti was a bit like a medieval kingdom. Barons ruled at each location. They each had their castle. There were serfs around, and boy did they fight with one another. It would be lovely to tell some romantic story of cooperation. There was bugger all cooperation. And I kept on exploring this to the point of tedium. Interview after interview. Are you sure you never met anybody from Gorton? Are you sure you never met anyone from Bracknell? Right? There was no cooperation. So it is a separate part of Ferranti. Furthermore, it's a different market. We're talking here about process control computers. We're not talking about selling to insurance companies. We're not talking about selling to scientific establishments and R&D labs. We're talking about process control. And finally, the design requirements of this particular computer are quite different to those of a mainframe because you're interested in real-time control. The computer has to keep working month after month without a break. It's not processing batches of items in air-conditioned rooms. It's operating in a rather tough environment. Okay, so what's the story that's going to unfold? I'm going to tell you a bit briefly about the analogue background at Wythenshawe. I'm going to tell you about Maurice's gizmo, as Derek Whitehead so eloquently called it, and that just about sums up what it is. I'm going to tell you about the first display at the first London Computer Exhibition in 1958. We can perhaps get Mark Walker to reminisce about the pegboard, and I'll then talk about some of the production difficulties that occurred and why it took so long to get Argus from a display object in an exhibition into actual commercial production and sale. Because it's surely a myth that everything goes smoothly from prototype to commercial production. This illustrates that familiar truth that cock-ups happen, and they sometimes happen in multiple numbers. So we're going to discuss the cock-ups. I'm going to talk about ICI as a lead user and the rather improbable truth that Fleetwood in Lancashire was one of the world's leading centres for computing in the early 1960s. If you went to Fleetwood now, you wouldn't believe it, and I'm damn sure they didn't believe it then, but it is an interesting story nevertheless. And I should tell you about a paraquat plant that was upwind of my house, and I was blissfully ignorant of that, which is probably just as well, given how dangerous the low temperature sodium-based paraquat process is. We're then going to turn to what you were expecting to hear, which is the story about Bloodhound 2. And that is when the story really begins to get unusual and interesting, because this is where we get round to chance and friendship rather than planning or strategy of the kind of thing that we love to talk about in business schools. How deluded we are. Okay. The major figure in all this, looming large, is Maurice Gribble, still alive and well. Spoke to him on the phone a couple of weeks ago. Born in Ipswich, I don't think he was a very conscientious school child, because as he said to me, he was always drawing radio circuits in his French lessons. And he didn't pass French, but ironically he's a now fluent French speaker, but that's to do with his good looks and an interesting French woman. He wanted to do electrical things. How do you do electrical things in Ipswich? It's hardly the centre of the global electrical industry in the 1930s. So his father volunteered him to be a pupil, that's to say he paid for him to get training in the local power station, which was a reserved occupation at the beginning of the Second World War. But he decided that rather than being bombed, he would rather volunteer for the RAF. He'd heard rumours about radar, because like all these top secret things, as we'll discover, they're often remarkably well known and widely known. And he went off and had a very interesting war, working on G-beams, for instance, and then came back and, like so many demobbed people, wanted an education and was fortunate in getting a University of London external degree, and was then duly recruited to Ferranti where his first job was actually working here in Exhibition Road on a kind of simple analog computer that Ferranti had developed to show how a computer could be used to solve problems. And so he actually started work literally here and went on to work on the Mark I, but got rather bored with trying to get a large ball printer working, and decided that it looked more entertaining to go off and work on what was going to become the development of Bloodhound, first at Boston and then at Wythenshawe. So Maurice is the delightful man who quite simply went out and designed computers. Let's be honest, I don't think anyone in Ferranti knew what Maurice was doing, or indeed understood what Maurice was doing. There are some wonderful anecdotes about him laying on lectures at Wythenshawe, which attracted a large audience for the first lecture, but somehow the audience is diminished as... I mean, he's a delightful and incredibly bright guy. Maurice developed...
He's 70.
Maurice had a number of really outstanding insights, but one thing he began to appreciate is that the emerging transistors would rapidly replace valves. And he was willing to take a bet on transistors improving. He's quite open about this. He said they were pretty poor when he first started, very low power. But he decided that he would tinker around with transistors because they had more stretch, more potential than valves. What is even more remarkable was that he was thinking in terms of going digital for missile control at a time when all the missile control was analog. Let me put this in context. There was a very enigmatic project called Blue Envoy. Blue Envoy was a surface-to-air guided weapon that was cancelled in 1957. But the idea of this is that it would have mid-course control from the ground. You'd launch it and it would be guided from the ground, unlike Bloodhound, I'm going to talk about in a moment. It would be guided from the ground over its mid-course by signals. So therefore there was a difficult problem of how do you send control signals from the ground to the hydraulic servos on the missile to steer it towards its target. And this is where Maurice thought that maybe one way forward would not be to use analog but to use digital. And I should say, if you think back to the context of the mid-1950s, 1955, this was an analog world. They built analog computers because everyone had to build analog computers in the 1950s. You couldn't buy them. You could buy the components, but you couldn't buy an analog computer in the mid-1950s. So Ferranti Wythenshawe were used to building analog computers, for instance, for simulation of guided missiles. So Maurice was there in an analog world where it was quite normal to tinker and build things. His breakthrough was to think that you might be able to do something with digital. After all, he had this radio ham background, he knew all about Morse code, that he might be able to tinker with digital, and that maybe, just maybe, transistors will be the way forward. So, like you do, he went out and built himself, as far as I can see single-handed, went out and built himself a simple prototype digital computer for the purposes of mid-course control of this command guidance guided missile. I shall show you some pictures in a moment. But the great breakthrough was that although it was cancelled, he was quite wedded to this little digital gizmo of his, what Derek Whitehead later called Maurice's gizmo. And an appeal went round. The Duke of Edinburgh is visiting Wythenshawe. I should say the Duke of Edinburgh was always visiting Wythenshawe because he was a great horse, the horse-driving fan, crony of the Ferrantis, and so they always were looking for excuses to get him up to Wythenshawe. So the Duke of Edinburgh was coming, And what occurred to Maurice was that he could use this very simple digital computer, which essentially was being used to solve trigonometric problems, but he could use this digital computer as a royal demonstration. Now, if you think about it, that is a political coup for two reasons. Firstly, you have the attention of senior management, albeit for 10 minutes, assuming the thing works. And secondly, you got command over all the resources of the workshops, because your gizmo has priority over everyone else's, because it's the royal visit. Of course, you can go back and find the minutes of all the preparations for the royal visit. Unfortunately, no photos. You can find the minutes. You know, what attention was being paid to this, who was going to see it. I can tell you, there are two obsessions. All the minutes relate to, one, the fact that it's going to disrupt the factory tea breaks, and secondly, that Dennis Best was deeply worried that people would be idle, standing around and gawping, so he gave strict instructions that everyone was to be at their bench and look busy, even if they weren't. Okay, so that way is history made. So he set up this demonstration, which was a simple idea of parallax correction. You have a red light, of course a missile target, on a screen, and the Duke of Edinburgh was invited to move a lever around so that a blue light converged on the red light. The clever thing, of course, being that the computer underneath the table solved all the problems of correction and caused the blue light to home in on the red light. In such ways are breakthroughs made. They did all the usual things. They, of course, developed the lights with the aid of headlight bulbs from a car. And how did they make it light sensitive? Well, they scratched the outside of the transistors. In that way, Maurice developed this gizmo, which, although it should not have had a life beyond the Blue Envoy cancellation, actually showed its worth in a royal demonstration. Photos survive, and you can begin to see from these photos the beginnings of Argus. You can see the NOR logic, the not OR logic, which I guess some of you from ICL 1900 series will say, yes, we recognise that. And the simple idea of using a flip-flop, which uses rather a lot of transistors, which were expensive at the time, but use a flip-flop for counting and multiplication and so on. All done, very low power hearing aid transistors. This is pre-radio transistors, OC71 transistors. This was given away to University of Manchester somewhere about 1960. We're still routing through storerooms for it. All I've found so far is a superb architect's model of Calder Hall nuclear reactor, but I haven't found this. But the appeal is still out. What he wanted to do, of course, he needed some kind of memory. So what he used was a very simple diode plug board, and you can begin to see the origins of the idea of a plug board being used for a memory. Whether it was the royal approval of the idea of a flip-flop, which captivated the Duke of Edinburgh, or whether it was just Maurice being more politically savvy than he appears, because he's a very gentle, kind man, and not, you would have thought, one to be able to operate the system very effectively. It was agreed that this had potential as a future line of business for Ferranti Wythenshawe in order to move, as Maurice suggested, into process control. Let's not get going on the history of process control computers in the States at the time, but it was an emerging market. And so what was actually called the process control transistor computer was then duly demonstrated at the first computer exhibition in 1958 and discussed at the Associated Symposium, Olympia, I think it was. And there are two things perhaps that are striking about this. The first one is that nearly all the major aerospace manufacturers in Britain exhibited computers at that exhibition. Every single one of them, except Ferranti's, was analog. So Ferranti, out of all that group, had already decided to switch to digital. And remember, this is not Ferranti at Gorton, this is Ferranti at Wythenshawe. The second thing is, of course, it was a kid's job. These boxes were not full of circuits, they were make-believe. It was a wish as much as anything. I'm not saying that there wasn't a complete design and components of a process control computer at that stage, but a large part of it was the kid's job. This is quite significant because the Russians were sniffing round. They were familiar with the fact that Ferranti Wythenshawe was a leading defence supplier and devoted considerable attention to soliciting Maurice's interest with offers of drinks and girls at the Russian embassy, which he clearly found, and he had a wistful look in his eye when he discussed this, he clearly found them very tempting. But of course he had a double reason for not cooperating with espionage. The first one was that he signed the Official Secrets Act, of course, as everyone had at Wythenshawe, no matter how lowly their role. And the second one was, of course, if he revealed the contents of the cabinet, they would be revealed to be chocolate boxes.
I trust they have flashing lights.
That's a good question. I don't know. I really don't know. But the principles were there by 58. That's to say, you had the principle of real-time continuous control. He had the notion of an interrupt. We can talk about interrupts at the end. Simon's much more expert than me on this. Certainly the idea that it should be reliable and robust to work in a works environment and a severe, dusty, dirty, hot environment. And it was going to be built to defence standards because defence too requires ability to operate at low temperature and very high temperature and industrial conditions. And here you have the difference between process control and mainframes. It would only ever need a single program. Because of course process control computers typically only ever need one program to control just one piece of equipment. That's not how it ended up in the end, because people realised that what they had here was a computer and they started adding on auxiliary programs and other problems. But the notion, the original design concept, was just one single program. And ironically, Maurice said he didn't think accuracy was that important, because after all, as you poll round every second or so, or fraction of a second, if you make a mistake in the arithmetic at one stage, you can pick it up in the next go round, and if it's a slow-moving industrial process, it doesn't matter too much. You're not going to alter the actuators too much in that fraction of a second. That was to turn round and bite him in the bum, because he actually then began to realise at a later stage that 10 bits wasn't accurate enough, and he got pilloried for wanting to switch to a 12-bit memory, but more of that in a moment. How did he get the Argus name? Well, this is virtually the only point where Ferranti Computers comes into the story. Because Bernard Swan was the very sensible, all-seeing marketing guy at Ferranti in London, important place, and he recognised that this Argus process control computer would complement the mainframes that they were developing in their product range, particularly at Gorton. So he could see a marketing opportunity, particularly since a lot of the major mainframe users, like Babcock and Wilcox or United Steel or Central Electricity Generating Board, would also be in the market for process control computers. So it made a great deal of sense to use a mythological name. You can look up Argus in Wikipedia, but essentially it's a totally unsavoury story of rape, murder, and that sort of thing that you associate with the Greek myths. Please read it. It makes you realise how less shocking our current age is than that of the Greeks. Although perhaps not in Athens for the last few days. As I've already suggested, the key features of Argus were essentially a sequence of innovations between 58 and 59, all of which seem to be traceable to Maurice. I mean, I've interviewed Maurice 3, 4, 5 times maybe. And each time you say, well, did you know about interrupts? Well, no, we didn't know about interrupts. We weren't aware of independent invention of interrupts in the United States until we came to investigate patenting, for example. It's quite clear that at that time, what was happening in Wythenshawe was in splendid isolation from what was happening in the United States at the same time. There was very little interchange of information across the Atlantic. This will crop up in another context. There was a degree of what you might call, I suppose, semi-parallel operation. We've spoken about the transistors, and fairly standard for that day, the use of a ferrite core memory, which was just then coming into use for mainframe. And I shall speak about the pegboard in just a moment. Those of you who are techies, and that amounts to all of you, will be interested in the design features. But where my particular concern is the difficulties of converting this prototype into a commercial computer. As I've already suggested, there's something of a myth that you take a prototype and the next week it's on the production line. That's a naive myth, as many of you in this room will know, and that's no less true of Argus. Let's take one example. Maurice had decided it was going to be an all-transistor computer, but of course higher power radio type transistors were beginning to become available, faster switching, and he went off to the radar research establishment and sought advice on which transistor to pick. They came back with a recommendation for a particular type of pi transistor, and Pi, I think it was Newmarket, a firm in Newmarket, the Pi subsidiary, agreed to this massive order and went off and decided that because it was such a big order, 10,000 say, that they would alter their manufacturing techniques in order to get some economies of scale from making these particular transistors. So they developed this new V101S computer with a, transistor with a soldered can at the end, and decided to speed up manufacture by dipping the can ends into soldering flux before they got on with the soldering. They then sealed the transistors with silicon wax or silicone grease, and supplied them duly to Ferranti. They built the Argus computers with these transistors, and after about 6 months, the computers started dying on them wholesale. Because soldering flux is hygroscopic, it loves moisture. The moisture took time to ingress through the silicone grease, so after about 6 months, it was just ripe for failure. So Maurice got the blame for that, because after all, he'd taken all the technical decisions about procurement, he'd taken the blame for that. But it illustrates this very familiar point, that it's a long step from prototype to commercial production. Of course, being a process control computer, most of the signals are coming in and going out as analog. So a large part of the computer is actually devoted to digital analog digital conversion. That's the nature of the game. But that doesn't seem to be too much of a problem, and ICI, for instance, as we'll see, we're capable of coping with that. Maurice developed his own machine code, but out of deference to some of the potential future purchasers who were familiar with Pegasus machine code, the machine code was rapidly switched not to from his, but to standard Pegasus order code, because that way people would be familiar with it and could make the transition from one Ferranti product to another. In fact, the customers probably made more for the transition from one Ferranti product to another than anyone in Ferranti. There you go. The computer had 2 memories. The ferrite core memory, which is a standard sort of random access type thing, and this headboard. Remember that Maurice's gizmo had a plug board with a diode plug board. This was an idea that which they had the patent, that you could effectively store a digital memory by inserting ferrite pegs, tiny little ferrite pegs about the size of a pencil, the end of a pencil lead, broken pencil lead, ferrite of course being a familiar ceramic. You could insert these ferrite pegs into the tray. So where you had a hole, digital 0, where you had a peg inserted, it was digital 1. Now, that's fine, but as you can see from the quotes, it's rather tedious because you've got these pegboards lined up and you put in certain pegs. And there are numerous stories of practical jokes. For example, Derek Whitehead denies that it was him that did this, but what they did to Pete Smith, one of the programmers of the launch control post for Bloodhound, was wait till he went out of the room, furiously polished the Perspex lid on above the ferrite to go above the ferrite pegs so as to build up the static electricity, and then come back and wait until his problem completed. He put the lid back and all the ferrite pegs of course did. But Mark, you have some wonderful stories. Enlighten us.
Yeah, but we used to write test programs for the actual Argus courses on the system. We used to try and do this and look up. It was just a bit away from the actual control post. I'm sorry, can we get take quite a long time to actually to sort of develop these programs, and of course we then took them outside to put into the Argus, caught by the wind or somebody opening the door at the same time, and you started all over again. It was you know, quite an interesting task.
So they were big and unwieldy, so they would catch the wind.
They were sort of about half a metre wide. I mean, like a very large tray. Literally, they were just loose pegs that we would use to run the test programs. The actual fixed program was actually lacquered in by this time. They moved away from the Perspex top for that very reason. But any test programs we took with were just literally loose pegs that we put in, a big box full of loose pegs, and off we go and try and program things in Octal.
And this is what RAF West Raynham, was it? Or?
Yes, yeah, RAF West Raynham.
And of course the layout wasn't really designed for carrying around computer components.
Well, technically speaking, it was all sort of as far apart from the next section as you could possibly physically get. So each missile section was some sort of a couple of 100 yards away from the next one, with all the missiles spread out farther away, so you didn't want them going off right on your doorstep. And so everything was sort of outside. The system was originally designed to be portable, so the fact that they could actually move it in a crisis. But the practicalities, especially by the 80s, was the fact that if you didn't move it, most of your cabling was ripped off and you'd start again. But yeah, it was all in sort of open spaces.
Okay, so that's this read-only memory. Of course, the process control computers only needed one program, so in a way having a semi-permanent memory, you're saying they were lacquered in, was in some senses quite a good idea. But it didn't persist. It didn't persist into the follow-up, simpler serial machine, the Argus 100. The talk of the day, obviously, in the late 1950s was automation. This is a magnificent quote from Magnus Pyke, who was as exuberant then in his writing as he was later to be on television. And he enthusiastically said, the new invention which makes the modern automatic factory different from the mechanical marvels which have preceded it is the electronic computer. Now in '56, of course, that was wishful thinking. But it was wishful thinking showing the way in which things were going to go, that there was an emerging potential market for automation. Indeed, automation was very much in the air in the late 1950s, early 1960s, and this was captured by a rather corny cartoon in the American Control Engineering magazine, which I'm told when I gave this paper in the United States was not politically correct and should not have been used, so I apologise for showing you a politically incorrect cartoon, but it captures very well this idea that what you really need is a marriage between computing skills, which are shown here by the groom, and just good old-fashioned valves and equipment that needs to be controlled which the poor bride is clutching as a bouquet. And the point that was being made was that this was a shotgun marriage, that computer manufacturers were not used to dealing with hardware that needed controlling, and therefore needed to be forced into this unfamiliar world of mechanical and electrical engineering. It was this unfamiliar world of mechanical and electrical engineering, not to say chemical engineering, that Ferranti was about to enter. And in every sense of the word, ICI was their lead user for incorporating Argus into process control. This is a rather spectacular mimic of the elderly, not to say ancient, Solvay process plant for making soda ash up at Fleetwood in Lancashire. It was already obsolete when ICI chose it for an experiment in computerisation, but it had many advantages as a sort of giant R&D lab. It had twin streams, so you could fit computerisation to one of the two streams and see if it worked before you duplicated it to control the other. And ICI Public Relations said the instrumentation needed renewing, which is just PR gloss. It had no instrumentation on it whatsoever. It just had good old-fashioned sight glasses and guys climbing up ladders and putting shining lights and things. And what Alan Thompson of ICI realised was that instead of having to put hundreds of three-term controllers all over this plant to control the valves, that you could do it centrally through one simple computer, and in that way save the expenditure of all the localised analog controllers for each of the particular valves. And for that reason, Alan Thompson was one of the people who was very keen to pursue this prototype installation. That's indeed the one we saw in the opening photograph, and that was duly installed at ICI Fleetwood. And ICI was something of a lead user, and went on not just to buy the Argus 200, which it installed at Fleetwood, which worked very reliably. In fact, the poor old maintenance man on standby there had nothing much to do. And not only did it work reliably there, but they decided to go out and almost give away half a dozen of the stripped-down Argus 100 developments, which were a cheap and cheerful serial version of the Argus 200. Now, of course, you weren't allowed to take photographs on ICI works, and you particularly weren't allowed to take photographs of their top-secret paraquat process using refrigerated liquid sodium and various other nasties, which was developed as a result of a pilot plant at Widnes. It was a small-scale pilot plant for developing this process for paraquat ions, and they then went out to build a giant plant by paraquat standards at Widnes. Now, the lady that I'm going to talk about told me, and I don't know whether this is true, that the reason they were keen to install a process control computer on this paraquat plant is that it was so dangerous that it would kill fewer workers if it was computer controlled rather than manually controlled. Since it was upstream and upwind of where I brought my children up, I didn't wish to know that, and it may well be apocryphal. But the fact is that this was installed, for example, here at the Pilkington Sullivan Works at Widnes. This computer, incidentally, survives in much modified form. In fact, it's a tribute to its success that it was much modified, because they soon realised that this was a very intelligent, sensible way forward, so they very quickly let a contract for increasing the computer power there. But this computer survives in a library store in Runcorn, if anyone wishes to see it. And this is just the control desk. As I say, these photos shouldn't exist. It was strictly off limits to take photographs on the plants, but if anyone wants a complete set of photos, they are available. The reason I stress this is because it's quite clear that there weren't just, as we'll discover, a large number of technically gifted males involved, There were also a tradition at Ferranti of having female programmers. Scylla says somewhat self-effacingly, this is because we were cheap. But when I interviewed the personnel manager, the rather formidable Emily Innes, she said, no, no, they weren't cheaper at all. We implemented equal pay at a very early stage. It's just that there was a prejudice that women programmers were much better. That may well be the case. So Scylla Breccia was responsible, and this is very typical in a way of Ferranti. Scylla Breccia, a new young ex-maths teacher, came to Wythenshawe and was immediately recruited because she'd had a holiday job programming in Mercury Autocode at Harwell because she happened to live outside the gates. She despaired of maths teaching and was duly recruited at Wythenshawe and promptly handed the job of programming this plant from scratch completely on her own, like you do. The manuals all survive. This particular manual, you see part of the photo, is about 4 or 5 inches thick, all handwritten of what she wrote. And this was the Ferranti way. There was a group of about 6 or 7 programmers who worked together, discussed problems together, and they were each given a plant to solve. But what's really quite interesting is that it makes you remember what it was like to program an early machine like this. Because recall that not only did you have to know what the instruction was, but you had to know the exact location in the memory. So your instruction was effectively both the instruction plus the memory location, and you also had to work out how long each operation would take. Multiplication, 1.87 milliseconds. Division took longer, of course, 2 milliseconds. Before you could then withdraw the result from the relevant store and put something else in instead. So with something like 8K of memory, you needed to be very careful. And it just makes me laugh, because you can imagine saying to a teenager, every time they touch an iPad key, they've not only got to touch that key, they've got to say where in the memory that particular touch would go and work out how long the operation would take. They'd laugh at you. They'd think it was totally absurd. But that is, of course, the nature of programming in machine code. Okay, let me move on very quickly to the archetypal Cold War weapon, which is Bloodhound. The Bloodhound guided missile was also being part developed at Wythenshawe. It was a guided missile centre. That's how come the research work was being done on Blue Envoy at Wythenshawe. This is a surface-to-air guided missile, and essentially the purpose of it was to defend UK Thor missile bases and UK V-bomber bases from attack by Soviet aircraft. And you can begin to see the parallels between process control and rocket control. A rolling mill, for example, this is Planworm here, which GE412 controlled. A rolling mill requires constant attention, constant modification of the roll gaps. It requires initial setup. In many respects, a missile is just the same. You've got initial setup and constant and almost instant modification of the path of the missile. We've certainly got to get the radar dish pointing in the right direction. You actually have maybe only 6 or 8 seconds if it's against a low-moving target. So they're very similar problems. It's not surprising. In fact, an American sociologist of the Cold War has made this rather caustic comment, sorry about the joke, but has made this rather caustic comment that the push buttons that were designed to make housework easier came from the same laboratories as the push buttons for guided missiles. He was actually talking about the United States. But nowhere was this more true than Ferranti at Wythenshawe, because after all they were developing the push buttons for guided missiles and helping computerise a soda ash plant that was essentially producing washing soda for domestic housework. So there was, during the Cold War, this ironically inglorious overlap between the two. There's a footnote to this. Mark Walker and I went round the launch control post at Duxford. I guess it's probably the only surviving one in this country. And there, tucked away in one of the cabinets, is, would you believe, a vacuum cleaner. No one on the launch control post team will admit to designing this vacuum cleaner. It's an installed, physically fixed-in vacuum cleaner, just so as you can do the housework in the launch control post at the end of the ship. Mark, you said you didn't have them when you were there. Is that right?
But I haven't, just tried to avoid using them.
Oh, you tried to avoid using them there. Do you avoid using them at home as well?
Oh yes.
Okay, enough of the irony. Let's get back to this Cold War myth. John Wilson, for instance, in his splendid books on Ferranti, there's 2 published and the 3rd's on its way, actually says this is one of the era's most celebrated adaptations of military technology to civilian use. Makes it all sound so simple, doesn't it? You develop a computer for the Bloodhound, it goes over and is applied to ICI. Isn't this spin-off? Well, no, it isn't that simple. As we're about to discover, it's a very messy story. It's a bit like what historians of technology like to call the linear model, the idea that somehow you put some science in at the beginning, you get some technology as the next stage, and then finally you get a product. Of course, anyone with an engineering background knows that quite often the technology and the engineering goes in first, and the scientists rush to catch up. After all, they didn't have thermodynamics for the first 200 years of the steam engine. It wasn't as linear as that. And nor did they actually have process control computers for Bloodhound, whilst process control was being used elsewhere. But there is a rather strange paradox to all this, which I've already mentioned, which is quite simply that everything's top secret. Everyone signed the Official Secrets Act. No one should discuss anything. But it was a superb environment for talking about things. Because you'd all signed the Official Secrets Act, you couldn't go down the pub and tell your mates. So what did you do? You had a good old gossip when you went to work and sorted all the problems out there and then at work. So there's this great paradox of secrecy that it almost puts a boundary, a wall around the people who are in the know and gives them a great opportunity for gossip, scandal and technical discussion. Bloodhound had a very long gestation. The idea of surface-to-air guided weapons began at the end of the Second World War, and prototypes and schemes proliferated. In fact, there was an abundance of them which had to be culled back, and there were even, for instance, competitors to Bloodhound, Thunderbird, for example. The idea was to link up the British Comprehensive Air Defence System, which had proved so successful, the sort of chain home load system, proved so successful in the Second World War, to a set of guided missiles which would shoot planes out of the sky and render fighter aircraft obsolete. In fact, by the Duncan Sands Review of the late 1950s, this was enshrined as official policy. Yes. And
that was what the plan was called.
Yes. And so this began life as a cooperative piece of research between Bristol, who supplied the engines, essentially the rocket motors, or Hawker Siddeley it would have been then, and the rocket motors, and Ferranti, who were going to do the clever bits, and EMI, some of the electronics. And what you have was, this is Bloodhound Mark 1, the first version, a twist and steer missile. If you want to know what a twist and steer missile is, just watch a pigeon coming in to land. All right? The alternative is, of course, a conventional sort of Cartesian monoplane, like a fighter or something like that. So a twist and steer missile with 2 ramjets on, which you hope don't go out, and that was a major problem, but let's not go there, and 4 booster rockets that fell away once the thing had lifted off. That was the original design, Bloodhound Mark 1. It had many defects, not least of which is it was trivially easy to jam the pulsed radar. Trivially easy, I'm told. It was very short range, it was all done by analogue, it wasn't fired in earnest, so far as I'm aware, and that's probably just as well. I don't think it would have worked that well. But what it did do was to act as a precursor for the really serious one, the Bloodhound Mark II, which is the one that we want to talk about now, which lasted in service from about 1964 to about 1991. I think the last was retired in the UK, although they continued on longer in other places like Singapore. Now this was an improvement on the earlier version. For a start, it used continuous wave radar, more of that in a moment, which was much more difficult to jam. And as we'll see, this necessitated a major switch in design from analog to digital. And this is what really interests me, because you ask a question, when did the world go digital? And this is one example of why and how the world went digital. Because of what historians of science and technology would call a presumptive anomaly. That's to say, it hasn't failed yet, but you know damn well it ain't going to work. So presumptive anomaly, a posh term for it ain't going to work if we carry on doing what we're doing at the moment. Let me explain the problem of a guided missile, though I have far greater experts present, so I'm a bit nervous about this. Essentially what you have is an early warning radar that can see the enemy aircraft coming, which transmits the location and bearing of the hostile aircraft, or aircraft plural, to an illuminating radar which puts a continuous wave beam onto the target. So the incoming plane should be picked up essentially by this transmitting radar, which will fire a very powerful radar beam at it. The reason for this is that the missile can then be fired and lock on to the reflected signal coming back from the target. In principle, it sounds a neat idea. You don't have to control the missile during its course. The radar dish on board at the front of the missile will pick up the reflected signal and home in on an interception point, obviously not on the plane where it is, but the plane where it will be. It will work out an interception point and shoot the incoming plane down. Principle, very simple. The central difficulty is that you have to set up the radar dish on the front of the missile. And I have to censor what Derek Whitehead tells me, because his language is so colourful that certainly for publication I have to censor it, but the tapes are outrageously entertaining. Anyway, Derek Whitehead is a character. Does anyone here know him? Let's say, okay. He has become a good drinking companion and is a formidable engineer in his own right. But what is really interesting about his career is that in many respects, none of what we have to talk about from now on was in his job description. And this is what I mean about communities of practice. When you have a problem, you often hijack the bloke or the woman who are best placed to solve that particular problem. Right? Forget what their job description is, forget what they're supposed to be doing, we'll have him, he can solve that one. Anyway, what Derek recognised is that there is no way that you could solve the difficulty of positioning this radar dish after unlock with the aid of analog. You'd have had to have a mass of resolvers and servos, and at each stage you're going to get a rounding error, the system's going to drift. There's no way that an analog system would be accurate enough to get the missile anywhere near the target. Okay? However, he had had something of an obsession with digital and had already developed a scheme for the air defence of the UK. Derek is not backward and coming forward. And he went off to get an audience with Norman Alder, who was in charge of the air defence of the UK, effectively at that time, to put this digital solution based on a Pegasus computer, which he had pioneered and trialled on a 2-week programming course at Portland Place. He put this scheme to Norman Alder. Norman Alder listened to him for just a couple of minutes at most and shouted at him, "There's no place for digital systems in radar. There isn't, and there never will be." It's one of the great prophetic statements. You know, of course they've been digital ever since. It's just. It also suggests, incidentally, that Norman Alder didn't have a clue what was going on in the United States with the SAGE strategic air-ground environment. Or else, if he did know, he didn't agree with it. So you'd think that Derek Whitehead would have been somewhat chastened by that encounter with God. In fact, he said it wasn't just like going to see God. He said God sat on Norman Alder's right hand. So you thought he would have been chastened, but he wasn't. Derek isn't the sort to accept defeat. Awkward, some might say. Now, of course, Derek was a drinking companion of Maurice Gribble. And he knew about Maurice Gribble's gizmo. He knew about the Duke of Edinburgh's demonstration. He knew that Maurice Gribble was working on parallax correction. He knew that Maurice had his gizmo, this hearing aid transistor control computer, which solved trigonometric functions like that in an instant. And Derek went, "That is what we'll do. We'll put Maurice's gizmo onto Bloodhound 2 to solve the calculations, for fixing, setting the radar dish at unlock after launch." We can discuss this in questions, but just a moment's thought will make you realise how difficult it is to fix this radar dish. You've got a missile going at Mach 2 in 3 dimensions. Okay, it's moving, the target's moving, and you've got to get this radar dish pointing towards the target to pick up the illuminating, the incoming Doppler from the continuous wave radar illumination. Correct to 1 degree. pretty difficult. Lots of maths. Needs to be done in a fraction of a second. Right. Okay. So what they did was to put, effectively, the Argus computer into this rather small, and as we've just heard, air-portable launch control post. Big computer, small launch control post, pain in the arse, because there wasn't much room in it, I guess, and I guess you were hugely relieved when they got rid of it, weren't you? So that was essentially the solution to getting Bloodhound 2 onto its target, was to adopt this process control computer back into a military context. So if you think about it, it began as military with Maurice fiddling around with his little hearing aid transistor computer for Blue Envoy. It had gone off into the commercial sphere and come back into the military sphere quite promiscuously. Forget Official Secrets Act, forget anything, it just wandered around promiscuously. The world was going digital. We're running out of time, I think, and in any case I'm much keener to hear what you have to say than hear what I have to say, because I've heard it before. But I'd like to introduce you to one last idea, which is this notion of how technology advances, how innovation takes place. Because as I've already tried to persuade you briefly, essentially what we have here in this launch control post is what sociologists call a community of practice. A little group of people who get together to solve a problem, a focal object if you like. They've got a common set of interests. You see this in families, you see it in teenage gangs. Only in teenage gangs you get respect by injuring and killing people. In the launch control post of the Bloodhound, you get respect by solving very, very difficult trigonometric problems digitally. But it's the same idea, that small groups of people get together. And notice, for instance, that Derek Whitehead wasn't part of the launch control post team. He was actually to do with the front end of the missile. But he just got pulled in to solve that particular problem. It's where the learning takes place. It's how engineers get together and tinker with things and share experience and share their tacit knowledge and get to do things. And so, in a way, when we think about innovation, we talk about firms, we talk about great people, we talk about inventors. But the actual reality is quite often just a community of 4 or 5 people getting together to chew some fat, solve some problems, a lot of gossip, a lot of scandal, and as Tom Lund said, we had a first-class team. What he meant was there was a community of practice. Okay, let me finish and very quickly talk about the subsequent development in about 1 minute. What is interesting, of course, is Ferranti was entering the process control market in competition with Elliott. They had a superb product. This is a testimony that came up when I was working on process control in the steel industry that was quite spontaneous from Alan Foss, who did a lot of the computerisation, for instance, at the Templeborough Narrow Strip mill. So they had an excellent product. The problem is it was just too damn expensive. Elliott Computers had this watchword, Eccles, because the Goon Show was popular at the time. It was their watchword, Elliott Computers cost less. And they did. Again, for the steel project, I interviewed someone who installed an Elliott Arch 102 at Dister Products on the outskirts of Liverpool. They went to see the installation at Fleetwood. They knew all about the Ferranti Argus 200 computer. It was just too damn dear. All right? Too damn dear, and so they went to Elliott's instead. Elliott's were faster on their feet, better at marketing, and cheaper. There was another problem too. You don't just sell process control computers, you also have the issue of providing software. And it was extremely complicated to write bespoke software every single project. When you were dealing with CGB or United Steel, this perhaps wasn't a problem because they had their own in-house software teams. But that wasn't always the case, and so one of the breakthroughs was that they needed to develop their own computer software. They had to stop thinking in military, they had to get the pricing right, and then they made some very substantial breakthroughs. Most notably in booking systems for BOEAC, which is another fascinating story about a community of practice in Ferranti that matched up their talent in cathode ray tubes, which were used in the Bloodhound launch control post, to their talent for process control computing. Okay, I'm keen to finish there to hear what you have to say, although I have a postscript. What can we draw, what lessons can we draw from this particular case of this particular computer? It was a moment when manufacturing industry and the military switched from analog to digital. It was one of those key moments, a hinge of history as I've suggested, when the world began to go digital. It was a moment when the world began to go digital with real-time control, that's to say the kind of control that you would now take for granted for anything from traffic light systems to air traffic control. I've tried to draw you into another area of computing away from conventional mainframes into another area, process control and the military. I'm sure that there are other parts that we could look at. I've suggested to you that during the Cold War there was really quite a complex relationship between there was quite a complex relationship between military and civilian use. It wasn't a simple story of spin-out. I've tried to suggest the ways in which innovation actually takes place, in this context in computing, but more widely in terms of small communities of people who often get together. And finally, of course, there is this hidden agenda that I would like to see more attention paid to Argus, particularly in the Museum of Manchester, but perhaps that will fall on deaf ears. One final request: Ferranti Argus computers are still going. There's a desperate need for spares if you have them in your garage or your loft, and a desperate need for technical support. So if any of you want to see me at the end, Thales in particular has put out an appeal both for parts and for technical support. But without more ado, I think that's it. Thank you very much.
Questions, comments, stories?
Yeah, I'll start off with my standard story. Back in the 1980s, we needed a system to answer the telephone to take orders from pharmacies around the country, and these were then processed in an IBM 360. So we sort of scratched our heads and came up with the answer for an event-driven operating system in a machine, IBM System 7. They then had to get these two things to talk to one another, which was done by writing machine code programs and all sorts of interesting things. But we had difficulties. So director phones up IBM and says, "What can you do about it?" They said, "Well, we're terribly sorry, but you're in a multi-supplier situation because DP made the 360 and GSD, the typewriting division, made the System 7, and never the twain would talk."
Hello, Simon Lavington. I'm interested in your use of the phrase hinge of history and key moment for analog to digital. It was a rather wide hinge, wasn't it? I mean, even if you take the aerospace field, the difference between the time at which the mission control, which is to say navigation, weapon systems, etc., then they switched to digital, and on one hand, and on the other hand, the time at which the airframe control, engine management, stability, etc. switched. There was a 10 or 15 year gap between those two, so perhaps it's not quite a key moment. The hinge is quite broad.
I agree wholeheartedly. I think that one of the interesting things is the fact that we could obviously go back to Jacquard looms anyway, or we could take it that far back. But one of the really interesting things is precisely this kind of issue. Why did some parts of the world go digital early, and why did others take an enormous amount of time to get there? And why did some retrogress? For example, I think it's Concorde, it was an all analog system, but there was much that was proposed beforehand that it should be digital. And the other point that I would make is that the two coexisted side by side, even in computing. Even at Ferranti Wythenshawe, there were analog and digital fans, and that was true in United Stills Research Lab, that there were analog and digital fans. And what's more, there were joint analog digital computers. And if you look at for example, the scheme for ICI Fleetwood, a major component at the centre of it is analog to digital conversion, and indeed the Bloodhound control post is a huge amount of analog to digital conversion. So you're not even picking up the full hinge, you're actually taking a little sliver out of it and saying that bit can be solved digitally, and then we'll go back to analog. But I agree with you, it's a completely messy picture, but it seems to me intellectually interesting to try and unpick that picture. Why did it happen in some areas and not others? And so when I went and investigated the launch control post, it was very clear that there was this problem of the presumptive anomaly. Derek Whitehead said it was the best decision he'd ever made in his life, which I think is a lie. I think marrying his wife was probably the best decision Derek Whitehead ever made in his life. But I mean, probably the second best decision he ever made in his life was to recognise that you couldn't get the accuracy. Now, the Thunderbird, the English Electric Thunderbird, didn't go down that route and had all sorts of acute problems of accuracy. So you can actually then begin to pick off these individual decisions when people decided to go digital rather than analog. But I don't know of a standard source. I mean, if you, for instance, read the chemical engineering literature of the late 1950s, there's endless debates about whether chemical plants should be controlled digitally or analog. And the jury was out in all sorts of areas. So unless I'm mistaken, I don't think there is a convincing story about the rather bitty and messy spread of digital. If you look at it in history in retrospect, we're all digital. If you look at history in retrospect, it's blindingly obvious we should have gone digital. But why did it take so long and why was it so messy?
It was because the people in charge didn't understand. I've been in computers since 1950, and most of my decisions had to be taken because my manager, or his manager, said we will go that way rather than this way, which I knew was the right way. That, I think, as you explained earlier on, the decision was made by somebody who didn't know it.
So if we'd all listened to Norman Alder, we'd solve this.
That's right. Yeah. We only need one computer in this country. It was a statement made by some politician. IBM got 100 orders for the American Air Force. Therefore, Ferranti had to do all its development and charge it to the customer. IBM charged it to the American government and then to God. That's basically it, I think.
Terry Froggs, I worked for Aylen Automation at the start of my career. A couple of things. Firstly, am I right in remembering the Bloodhound project was ultimately so successful compared to any other government project that I can remember that Ferranti were asked at the end of the day to pay some of the money back to the government? That was a rare event. Secondly, can I recommend that anybody who has a chance actually goes and sees the inside of a steel mill? To see a cubic, 10 metres each way of steel coming in at one end, flaming hot, and going out as a railway line, a quarter of a mile, a chain long, whatever, at the other end, a mile away, to see that all of this railway line, as it gets rolled, has to keep moving, because if it doesn't keep moving, the rollers it's on will melt underneath it. And to think that the computer has to keep controlling all of that, and if the computer stops, the whole place basically welds into one solid lump of steel. It really is a tribute to the success of the computer, the reliability of that machine in that era.
Yes, I mean, you are right that there were major excess profits made on Bloodhound 1. And the reason for that was to do with a very clever man called Bob Grove, who was an excellent production manager. Ferranti had lousy cost control, they had no accounting in-house, and they put everything in on the basis that highly qualified graduate technicians would be needed to assemble Bloodhound 1. Well, Bob Grove, who was a very efficient production manager, realised that the local mill working women would be much better at this task than anyone with a graduate degree, which completely unqualified them for the job, and managed to produce these Bloodhound guided missile forebodies at a much lower cost than they'd anticipated, and someone duly found out that they were indeed making a huge margin, of which I think probably Ferranti were almost blissfully unaware, because the Ferranti were breathtakingly incompetent. Ferranti as a firm was run on the basis, quite simply, of if it's interesting technology and it looks like fun, we'll develop it. So part of this story that you're saying that there was no opposition to digital, I repeatedly heard during these interviews that the bosses at Ferranti Wythenshawe had not a clue what was going on. So these little communities of practice could go away and develop what they wanted. And secondly, when they did have some inkling, like Dennis Best, when he wasn't worried about the tea breaks and the workers looking idle, was actually willing to puff on his pipe and take a punt on it. So, I mean, it's almost outrageous what Maurice Gribble got away with. Maurice Gribble repeatedly said to me, I don't think anybody knew what I was doing. This in the commercial company, right? He was, yes, in the 50s, no one knew. If they fancy going out to build an analog computer, they went out and built one. Now, that is, of course, at one and the same time, the way to hell in a handcart as a commercial proposition. On the other hand, it's just a great way to generate creativity at a time of rapid technical change.
I went to France in 1968, went to Blacknowledge,
Mm.
and I was starting to work on a computer which was being designed.
Mm-hmm.
And it was being designed using Maurice's law logic.
Yeah.
So I think your statement that the Ferranti departments can talk to each other is a little bit extreme, but I accept that it's 99%.
Maurice did say to me he went to Bracknell once. He actually went to Bracknell more than once, because I pressed him on this. He got told off. He got censured. He got censured for talking to the enemy. Yeah. He told, I mean, poor old Maurice, look, I mean, I really feel for this guy. He's a lovely guy, and we've drunk beer together more often than I think. You know, it's just lovely sitting in Abigail with your feet up drinking beer with Maurice. It's just great fun. But I mean, he really took some stick. He took some stick for talking to other parts of Ferranti, and he took some stick for picking the wrong transistors, or picking the right transistors, but then they pulled a fast from the manufacturer. And he took a load of stick for walking in one day and saying, I don't think it's going to be accurate enough. We're going to have a 12-bit instead of 10-bit memory, so therefore we're going to have a bigger ferrite core memory. He was the fool guy. I mean, he may have been able to get away with anything he wanted to do, but he was a bit of a fool guy, I'm afraid. And there were some really nasty characters around who made sure he was a fool guy. We won't name names quite soon.
I'm sorry, can we, I'll come back to you with the microphone in a second.
Okay. In 1975, I was working with Kodak, and I was in a small computer group, and I was assigned the task of working with the process control machines on their new coating track. The machines had been in place a few years. These were Argus 500s, and they were not great fun to use, actually. Only 32 instructions, and they did the job. And they were with Kodak. There was a huge building built in about 1970, I think. So that's when the machines came in. The top got liquid kettles that we poured little emulsions in, flows down through the various ultrasonic bubble removers and so on, all controlled by the Argus, right down to the basement, where it actually spread very thin, 4 or 5 layers at a time on the bottom. It's a continuous process. They didn't need an awful lot of looking after, but I've got a souvenir. There's a program which doesn't work with damaged tape, but I thought when I left in 78, I just this was just a souvenir. And in 78, I did prepare for them all the date change tapes that were going to be required, up to about 1995. So I thought that's about as far as we could go. They actually saw Millennium in it. I met my old boss recently. He said, no, we saw Millennium in it. So that wasn't.
I decommissioned it in 2006.
Did you?
Yeah, we're still working in 2006.
So that was a 26, you know?
It's about
I mean,
500s.
2006 we decommissioned.
Still running.
Yeah.
Can I say it's no?
Switched it on.
If I'm well, Humphrey, let's.
Can I ask a question? Was it decommissioned because the discs, the Burroughs discs, failed? Because that's why the big one at Huddersfield was decommissioned in the 80s, late 80s, because spares could not be obtained with this failed.
It never failed up until 2006, but it was decommissioned due to the fact that we couldn't get spares, and the only guy that we could find to program it, we had to pay £10,000 a time to come over here.
Right. Guarantee if it failed, you were in problems.
No, they upgraded the coating system that you just described, and we went to discrete PLCs that were based in local areas, so it gave us more flexibility on the control system. That was basically why. They upgraded everything. It was a £100 million project to replace all the systems, and it just was too old to leave. We didn't have the parts, so it got switched off.
Oh.
I think it's still there.
Right. Still there. We have a sorting parts.
Well, yes,
it was too big to get out. It
Tarlays will be very interested.
Because it was on the 7th floor, I think. So. get together afterwards.
I'm just intrigued about resilience.
Hang on, look to it.
I may be wrong, but there are people here who will correct me if I am. I seem to remember that on Atlas, the extra codes were represented, the code of the extra codes was represented by ferrite cores with inserted digits on it. Was that the same technology that is used on Argus? And if it was, does it indicate that at least there was some cross-fertilisation between the different fiefdoms within Ferranti?
I'm pretty sure I know the setup, and I'm not a techie. There is a patent to do with both Ferranti and our university relating to that system, and I asked Maurice, was that anything to do with you? Did you know anything about it? And he said, no, it wasn't. And I tracked down Maurice's patents, which are listed in the paper if you want them, and they're not quite the same thing. They were independently invented within the same company, as I understand it. Your one I think is Kilburn and someone.
Yes, it was.
Yeah, Kilburn and someone is the
Kilburn
patent.
and Grimsdale, and the Atkins one had copper keepers, as well as the
Yeah, Simon and O'Farrell, you were there at the time. Yeah, it was effectively the university. Yeah. I did track down that pattern because I thought, they did get together.
John, mine's more of a question. When you've got a real-time system going like this, you've got to have things like resilience, hot switch over, back up in a hurry. How did the Argus do all this? I just heard about two being.
Yes, they were.
But how do you switch them over? That was like
over the mark, I think.
The older 200 you did if the computer failed.
Is this on for you? Oh, sorry.
Yeah, with the 200 system, if the computer failed, control failed. But it wasn't. It was actually controlling the missile systems, not a process. So if something did go wrong, you would lose control of the radar. They would take you back. Or if the missiles, you just didn't send them the correct bearing. So it was fairly serious in the sense that we had to quickly try and resolve it, but it was still working on one system. And I think even on the upgraded version, that was still a single computer control system. So there was no real redundancy or backup to that system. Other than the software on the 200 was on a fixed program on the ferrite pegs. You just had the one set. That was loading the cabinets, and it was a tape backup on the later 500 and 700 systems. So, but there was no parallel processing or anything. It wouldn't take over as a backup. It would just used to fail, and you'd have to fix it.
So you did weld these steel mules together. Then, if you've got a power supply failure,
each site, each missile section had its own independent generator set. So each section would power up from that. So in exercise, bearing in mind this is the Cold War, if we were sort of under threat, we would immediately start up with diesel generators. We used to have on some of them 2 diesel generators. We could run the system on one, but to run all 8 missiles per section up, you needed 2. But you had some sort of redundancy there. So it was all diesel backed up.
I'll make a comment on the most of the chemical plants still have their 3-tone controllers. So if the computer failed, you could you just went back to 3-tone controllers on the plant. As you got to the 500s, we had 500s with BGD8s. So you designed it so it could be run partially, could be run manually. And with what computer? This on. Yes. What computer was actually left? These were batch plants that you could step it through from the control panel. It was slow, but it would run without the computer. Does that make sense?
I also programmed an Argus. Well, I had a slight involvement with an Argus 500 in about the same time, 75, and that was with the gas control system. And they had 2 machines, which I think automatically switched over between the two when they failed. I didn't have very much to do with it, so I don't really know very much about it. I was more they also had 2 UNIVAC machines, which were presumably backing up some data or something or other, and my job was when one of them switched over to make sure the other one switched over, or make sure that the live Argus was talking to the live UNIVAC and not the other way around.
I also wanted to say about, you were talking about how Ferranti were sort of financially competent, or financially weren't very well aware of what was going on. I'm sure that they may well have been much more financially incompetent than a lot of other firms, but I think I suspect that wasn't very uncommon. I mean, I certainly remember a story of STC selling telephone exchanges to the post office, or whoever it was at the time, and they'd just make up a number for how much it was going to cost. And after a long time, they decided that perhaps they'd actually better work out how much it was costing them to manufacture the exchange, and what relationship that bore to the price they were quoting. And they discovered that the nice polished desks that the girls sat at to plug in people's phones, they made a huge profit out of those. Every time they sold another one of those on a particular exchange, huge profit. Or other things, they were making massive losses. I suppose it worked out in the end. After they worked out how much it was costing, their accounting practices were corrected to take account of that. But I suspect that it wasn't just Ferranti. I suspect it was fairly universal.
Well, you're out for
This is a question about innovation and the flow of ideas. One of the follow-ons that's attributed to Maurice is the pickup in Canada, where a whole range of computer developments were had. And I'm not sure whether that flowed direct from Maurice visiting Canada or people visiting him, or whether it came through digital systems at Bratton. Any comment?
No, I haven't, because the great danger of all research interviews, there are 2 dangers in research. One is you go into an archive and it's full of such interesting things that you never go to research what you want to research. And the other thing is you go and interview someone for a day or 2 or 3 days in the case of Maurice, and you end up discussing what he was doing in sonar radar, yes. I do know from Maurice's written material in the archives that he was involved in this Norgate design, and that then went to Canada with, is it Packard? Ferranti Packard, and then that came back, I guess, from the 1900 series. So he is writ large over a number of technical developments, but I thought you've got to have focus here, otherwise you're going to go off and...
It's just that the North Americans seem to be a bit more ready to pick up new ideas. The Canadians, I suspect, were faster moving than other parts of France.
I really don't know. I would hesitate to say that. What I do know from working on process control computers is that there was an extraordinary range of innovative developments in America and the UK, also at Elliott, between about 57 and about 62. But there were also many casualties. I mean, people say, well, look, Ferranti and Elliott eventually fell out of the game, but so did almost every single American company. And certainly a lot of the precursors, particularly GE, for example, a lot of the other, Westinghouse, Bunker Ramo and so on, they all dropped out of the game. So actually Ferranti, in global terms, did surprisingly well, as did Elliott, doing surprisingly well in global terms, yeah. So I wouldn't generalise on who were the most innovative. I'm pretty sure that in terms of process control, that Westinghouse were probably about 12 months ahead. But that's as far as I go, because that's all I really know about. I would love to know more about the American guided missile systems, but they seem to be a lot more analog based and slightly earlier than Bloodhound 2.
Yeah, actually the last system to be running in the old control tower at Heathrow was a
Argus 700 based message switching system. That was probably one of the last going forward message switching systems running in the country before it was replaced by sort of packet switching technology. And it actually ran on a bit because the successor system was late. And it succeeded in Argus 500 based message switching system, which but it still agreed. The 700 was actually extremely late. So one of my friends was actually kept on for 4 years after he wanted to retire because he was so late with the replacement system. He was the one and only man that knew the 500. And then, of course, the Argus 500 was late as well. And it replaced nearly a 4100 based switching system at Croydon, which is the last thing that kept aviation at Croydon going. I've got this long history of the British computer industry doing interesting things, but not really to time and to budget.
Yes, and of course, what you forget is that there's, so sorry to repeat this point, but there is a long step between sketching out and developing the prototype and converting it to commercial productions. As we've seen with this problem with transistors, late modifications to the design over the ferrite core memory. These are the kinds of things that cause programs to slip by a year or 18 months. And quite often it is just good old-fashioned production management of innovative new products, yes.
Just to my museum hat on, the machines themselves aren't being lost. The last message switching system came out of Hounslow Park about 3 or 4 years ago. That's an Argus 700 and that's saved at the museum. There's also quite a few Argus 500, 600s come out of radar stations in air traffic control. So they are all being kept. But if anyone's interested, we are looking for a champion to curate and look after them and present them.
My particular beef is the fact that the Museum of Science and Industry at Manchester have a 200 from a launch control post and a couple of hundreds, and you can't even get to see them no matter how much you grovel, which I find is rather incomprehensible. If you research something for 5 years and you can't even see an artefact that's being preserved so that scholars can look at it, that seems to me an absurd paradox, really. For the gold.
The Argus 200 was still used on the Bloodhound system from about 1985, 1986. So that was actually served at least 20 years.
Yes. I can give you an absurd example. I came back from New York about a year ago and got an urgent email from JFK Airport, which I just left, saying, our GE412 has gone down, can you please help? So this GE412 had been installed in about 1965, and this was 2001, and apparently it had been running without fault or blemish since 1965, and they just now had a fault. And it's responsible for pumping half the aviation fuel at JFK Airport.
I can't be many people had experience of fixing the problem.
No, so I actually was able to help them and suggested that they contact Steven Spielberg's dad, who designed it, which is of course what a Julie did.
Are there any Arguses still in use?
Yes, that's why I don't think there are any Argus, very few Argus 200s were built. Most of them went into the launch control post. Quite a lot of Argus 100s were built, but I think they've all been discarded. But that's certainly why Kevin Vibert of Tarlays is interested in recruiting people and recruiting parts, because there are quite a lot operating. They wouldn't let me see the one at Dungeon XB, for instance. They thought I was a terrorist or something, but probably right. These academics aren't to be trusted. But so I suspect there are quite a lot still going in nuclear power plants, yes.
Get rid of this. I was responsible for the 200 at West Thurrock.
Oh, excellent.
Two words haven't been mentioned yet this afternoon, which is very much about in those days, are quality assurance. And we had one interesting episode, I believe, a transistor failed in the Argus, and it was one that controlled all the output lines, and it set them all to 0, and everything stopped. All the fans, all the pumps, all the valves, everything. Safety valves blew,
whistles blew and sirens and things all over the power station, and we learned our lesson on that. CGB or Ferranti and Babcock together. So one of the highlights of the
Can I say, I haven't mentioned West Thurrock. ICI worked the first process control application to purchase an Argus 200. It was Babcock and Wilcox for the CGB at West Thurrock, isn't it? But the central problem is that the power station construction was delayed, as I understand it. There were a lot of large site problems in Britain in the early 1960s. And that Ferranti, that Argus 200, which should have been, I guess, the first to be commissioned in a civilian role, or the first to be commissioned, actually went into store for a long time, as I believe.
It is, yes.
Yes, because Ferranti charged for the storage. I came across that account, they charged. And they were also pretty, if I may say, pissed off with the spec, because all the inside of the cabinets had to be painted white, and all the cable runs had to be labelled, and this caused an enormous amount of bother.
Because it was a CEGB standard.
Yes, yes. But this is actually why they got the Pegasus order code on there, because Babcock and Wilcox was a very keen Pegasus user.
I thought it was one of the designers at Wythenshawe, Mike Eyre, who was doing detail work, was so attracted by the Pegasus order code, especially one or two particular orders, and he wanted to incorporate them.
Well, I'm sure Mike Eyre played a large part in implementing it, that's true.
Indeed, yeah.
Yeah. I've not gone into the sort of the first lieutenants, but Mike Eyre was definitely one, Dave Senior was another, Dave Butler was another. There were about 5 or 6 people in this. Yes, so there were about, I've talked about communities of practice, but they were developing the Argus 200 into a viable machine. There were a group of you've suggested, about 4 or 5 people who converted Maurice's drawings and prototype into a commercial machine. I mean, there are all sorts of problems, like the fact that it was minus 6 volt and 0, but actually the machine was sort of live, so it was more like minus 6 volt and plus 1.5 volt. So there are little local difficulties like that people like Mike Eyre and Dave Butler and so on solved.
On the topic of the order codes, might not the marketing man have had a say with the parents, as well as when they were discussing the name, might they not have...
I'm sure that getting the Babcock and Wilcox order, rather than the ICI order, Babcock and Wilcox spoke to Wythenshawe before ICI. I'm sure that would have swayed them. To get that reference plant is quite a coup, isn't it? If you're entering a new market, like process control, you've got to have that reference. And so they would have, I'm sure, done anything to get the Babcock and Wilcox order. But as I say, ironically, it was really ICI that became the lead user that drove Argus forward because of their commitment to having this complete digital control of this obsolete plant up at Fleetwood. So things don't always turn out as you anticipate, but I'm damn sure the commercial people at Portland Place did have a say, yes.
So that's something you can put in the process.
Yes, yes.
I can remember working at Newman Street in the sales department around it would be about 1960. John Davidson had something to do with Argus. What he was doing, I don't know. I don't think he was going on.
This is a computer department catalogue, 1960.
And it does have,
that came from Newman Street or Great Portland Place, wherever they were at the time.
And does it have the Argus under its name Argus, or as a transistor process
control computers?
Oh, well, that's, yes. I think they adopted the name about maybe August, September 59, something like that.
May 1960.
There you go. Yeah. So it's August time.
I think we probably are at the point where we Alan, the final quick one.
There were other real-time proponents in Ferranti, particularly to do with air traffic control. And what's his name, Johnson, Harry Johnson, around at that time as an influential figure encouraging Ferranti to get more into real time.
Oh, I'd have to follow that up. Right. That was Hermes and Pegasus then.
I think probably at this point we'll call it a day. I sense there may be discussions to go on. And there are there are places of refreshment adjacent to South Kensington Station where someone of us present retire following the meeting. Can I first of all thank Jonathan for a fascinating afternoon, and I think the amount of input and discussion and so on from you all indicates the amount of interest that people have got. Can I just say once again that next month's meeting, which is on the 15th of March, is on Turing and his contemporaries, when the 4 contributors to the new book will be presenting basically a short overview of the relationship between Turing and his contemporaries as they see it, and Simon Lavington will be acting as the he will bring the various strands together, I think is probably the best way of putting it, as well as making a staunch defence, no doubt, of Manchester's position as well. But next month then, Turing and his contemporaries. The April meeting, we will be, in fact, once again actually, again in the Northwest, talking about Barclays Bank and technological change, looking at the way in which Barclays Bank had to adapt in order to bring computing into the centre of their activities. That's the April meeting with Ian Martin and David Parsons, and then we will have a second meeting on different aspects of the life and contribution of Alan Turing in the May meeting with Brian Carpenter. So let me conclude by once again thanking Jonathan for a fascinating afternoon.